Hello, everyone. I'm Yali Yang. Today, thank you for the organizers for giving me this opportunity to show my work. And the collaborator of this work is Dr. Hongjun Xiang from Fudan University, Dr. Hoge from Nothenburg, and Dr. Laurent Blesch from University of Arkansas, and Dr. Wei Ren from Shanghai University. And this work is supported by these fundings, and this work just published on PRB last year. And today the topic is improper ferroelectricity at antiferromagnetic domain walls of perovskite oxides. Today the compound I focused on is samarium ferrite. We know it's orthorhombic. It's G-type antiferromagnetic, and the ideal temperature is 670 Kelvin, and the structure looks like this. And from the space group, we can know that it's central symmetric, so it's nonpolar. But an interesting report in 2011, it reported that it reported a polarization with magnitude 0.01 μc per cm square induced by Si cross Sj type candidate AFM ordering. But later in 2012, a comment says that the proposed magnetic structure by ND cannot give rise to the observed electric polarization. And later in 2012, D replied that they agree with the comment by Johnson, and they suggested another Si.Sj type exchange restriction mechanism to induce this polarization. So we know it's the effect of the polarization is still unclear and under debate. So we would like to explore if specific mechanism can induce the polarization in this samarium ferrite, or more generally in rare earth ferrite or rare earth chromite. And the method we use the density functional theory, and the software package we use WASP. And regarding the relaxation, we fix the lattice parameters to be experimental ones, and relax the atomic positions. And the polarization we calculated by using a Berry phase method. And also we use a recently reported unified model for the spin order induced ferroelectricity to do further analysis. And the structures we use, you can see here. From these structures, we can see 4 single domain. We use X0 to represent the G0, C0, A0, F0, which means the magnetic is G-type, C-type, A-type, and F-type. They are single domains. And other structures are constructed by considering 2 antiphase boundaries of magnetic domains and alternating along C-axis. Yeah. So here we use XNM to represent the other structures. And we take G22 as an example. We can see there the green plane represent the magnetic domain wall, and the blue and red arrows represent the spin up and spin down. So we can see in each domain, it has 2 FeO2 layers, which means the N and M are both equal to 2. And here, let's see the resulting space groups. Here we can see the the resulting space groups can be divided into three groups. One is PBNM and P21/C and PMC21. Here we can see for the single domains and the domains with N and M both equal to odd, they are PBM and they are non-polar. And with XNM, with N and M are both odd, but they're not equal to themselves. So they are also non-polar. But if the N and M are both even, you can see they are polar with PMC21 space group. And we can see the magnitude of these polarizations. So we can see in agreement with the last slide, when the N and M are both even, we can see the polarization with this color bar. And if the N and M are both odd, there will be low polarization. And we can see if we do a summation of this N and M, with increasing the summation of N and M, the polarization will decrease. Yes. So this four figure correspond to G-type, C-type, A-type, and F-type magnetic domains. So we can get a small conclusion here. The P equal to 0 when there is no domain walls. That means the single domain, and with the N and M to be odd for the XNM structures. And there will be polarization when the N and M to be even, and the polarization will along the B axis. So we further do the displacement of these structures. Here we take G33 and G44 as an example. When we analyze the displacement, we find along A and C axis, all the atoms can have displacement, but the late displacement will be 0 if we look entire this superlattice. Here, if we look along the B-axis, the displacement of oxygen ions located as the domain walls will have larger displacement than the other ions. So we first look at this G33. We can see the displacement of ions, of oxygen ions located as two domain walls, then move opposite to each other. So finally, there will be cancel. So there will be low polarization in this G33 structure. But if we look at this G44 structure, the displacement of the oxygen ions then move together to the B-axis, which will result in a late polar along the -B direction. And this is in agreement with our DFT calculation that this G44 structure has a polarization along -B direction. Yes, and we can see the space group of the G33 is PBNM and nonpolar, but the space group for this G44 is PCA21. It's polar. Yes. Okay. And as we said, we use the recently reported unified model for the spin order-induced ferroelectricity to further analyze this mechanism or the origin of this polarization. And this model based on the symmetric exchange friction mechanism, the SI.SJ, if we do a summation of the polarization, we can get the equation like this. And we do the summation in the entire superlattice, we can get the polarization in the form of this, the pxnm equal to 8b slash the volume, when the n and m to be even and the polarization along b-axis. And with the n and m to be odd, there will be no polarization. And we do further calculation, we can get the values of these polarizations. These polarizations can in rather good agreement with DFT calculations. So further, we considered another structure called G22 prime. This is a sister structure of the G22. We can see the difference between these two structures is just shifting the domain wall along C-axis. Yes. And using DFT calculation, we can see the energies for total energies for these two structures are the same. And also they have the same magnitude of the polarization and with the opposite direction of the polarizations. And using the unified model analysis, we can also get that the polarization for this G22 is minus 0.064 μc per cm square. But for this G22 prime, the polarization is 0.064 μc per cm square. So we can see they are the opposite to each other, but with the same magnitude. Yes. So we can get a conclusion that the polarization can be reversed by shifting domain walls along C-axis. We want to confirm that or check that if our finding can apply on other perovskites. So we checked the bismuth ferrite and rare earth ferrite and rare earth chromite, and we can see for the Nm to be both even, it will be polar. But with the single domain or with N and M are both odd, they will be nonpolar. Yeah, so we can see the general finding for this bismuth ferrite and rare earth ferrite and rare earth chromite. Yes, we do this confirm. And we also consider this string effect, which means we do fully relaxed of the structures. And we can also get the conclusion that there will be no polarization when N and M to be odd and the single domain. But there will be a polarization with N and M to be even and be along B-axis. So these values have the same qualitative properties as fixing the lattice parameters to be experimental one, and the different quantitative of the polarization. Yeah. And here is the conclusions. We can see domain walls with even N and M can induce this polarization, and with the order of 0.01 to 0.1 μc per cm square, and with increasing the sum of N and M, the polarization will decrease. And the improper polarization is related to the motions of the oxygen ions as the domain walls. And the unified model for this spin order induced ferroelectricity demonstrates the polarization arises from symmetric magnetic exchange mechanism due to the magnetic domain walls. And we also determine the quantitative effect of relaxing the lattice vectors on properties of these magnetic multi-domains, and the qualitative effects are the same. Thank you.
Thank you. We have time for a few questions.
I just have a compliment. For me personally, that work was the best I read last year. You have to understand that the experiments were done partly in my lab in Cambridge, and the objection was from very good people at Oxford. So this is automatically a serious fight, and you guys just solved it perfectly.
Thank you.
I applaud the work, and I thank you.
Any other questions or comments on that note? I had one quick question, actually. I was a little bit confused at the part where you mentioned about reversing the polarization. I don't know if you could just comment on that quite again.
Yeah. Here we shift the domain walls along the c-axis. If we shift it, we will get the polarization reversed.
Okay.
Yes. And the layers of the Fe2, the number, we shift by one layer.
Okay.
Yeah, or three layer. Yes, it will be reversed.
Okay.
Yes.
Okay. Thank you.
Yes, thank you.
All right. Well, we'll invite the next speaker to come on up. Okay, so thank you very much. So next we have another contributed talk by Yukio Sato, who's going to speak to us about in situ electrical biasing at the nano and atomic scale.
Thank you very much for introduction. My name is my name is Yukio Sato from Kyushu University, Japan. I'm going to talk about our in-situ TEM study, and more recently, we are trying some atomic scale in-situ study for ferroelectric and dielectrics. And because this is my first time to come to this conference, I'm going to talk about a little bit early data we have published several years ago, and also in the last half, I'm going to talk about our recent studies on in-situ stem observation of dielectric and ferroelectric crystal at high precision. So probably I don't talk much about this already because many of you already know about this crystal very much. So PMN PT crystal is a solution of PMN and PT with having perovskite crystal structures, and for the so-called MPB composition, this material exhibits very high piezoelectric constant. And because of this excellent piezoelectricity, this material is used for medical imaging devices. And in terms of its crystal structure, it has been reported that monoclinic phase exists in the MPB compositions. On the other hand, in terms of its domain structure, it has been reported that ferroelectric domains scale down to nanometer level. As you can see here, the In the case of MPB, PMMPT, the width of the periodic domain is roughly about 10 nanometer or so. Then the important question should be, how does this ferroelectric nanodomain respond when external electric field is applied? And I believe that prior to our study, the response of nanodomain had not been observed in real time. So in order to visualize that, we have used I'm sorry for that. We have used electrical biasing institute TEM. As you can see here, in this method, we can apply external electric field to the sample while observing the specimen with TEM. And for this purpose, we have used commercially available TEM holder, and we have designed special test fixture for this purpose. And by using this method, we can observe the internal structure of material with high spatial resolution at the nanometer scale at this experiment. And also we can do this observation in real time. In this particular experiment, the temporal resolution was 1/3 second. And then let's move on to the results. This image shows that the domain structure right before we apply the electric field, and its domain structure schematic is shown here. In this field of view, there are 3 different microdomain bands, and each microdomain is composed of training of lamella-like nanodomains. And for this sample, we applied electric field, and the movie starts here. And now the electric field is off, and now it is turned on. Then right after when the electric field is turned on, the domain structure changes, and after it is removed, that it comes back to nearly back to the original state. And this kind of response can be repeatedly observed on the apply and release and the electric field again and again and again. And this is a domain structure during the electric field is applied, and the domain structure changes from this state to that state. And when the electric field is released, this domain state nearly comes back to the original state. So what we find is that the change of structure is the dominant process of the structure change is a domain reorientation of the domain. And also another important thing should be that even after high electric field of this much, the high density of domain will still exist like this. And we also found that the domain structure is reversible on the applying and release of the electric field. And we have repeated this experiment for the different biasing directions. The top half is for the electric field along 100 direction, and the bottom half is for the 111 directions. And we have again observed very similar results. So before biasing the electric field, the domain structure is like this and like that. And when it is applied, the domain structure changes nearly in a single microdomain band. However, the high density of nanoscale domain will still exist. And when the electric field is released, the domain structure nearly comes back to the original state. So we found that commonly to the different biasing directions, we have observed similar behavior of domain structure changes. And after we published this paper, I have got many question many times about its crystal structure of our sample because after these studies, and so, first of all, because this material possesses this sort of very tiny domain structure, so this situation complicates the understanding of crystal structure at the single domain levels. So then after this study, the number of reports has been published for the crystal structure investigation, and different papers reported different conclusions. So we decided to study the crystal phase of our sample by ourselves with our method. So for that purpose, we have used electron diffraction analysis in TEM. So here's some experimental detail, but because of the time limitation, let me skip most of this. However, one of the things that I emphasize here is that we have measured electron diffraction pattern very carefully, like this. This is one example of the observed pattern. And then the distance, the individual diffraction spot was analyzed very carefully, particularly the distance from the origin, 000 spot, was carefully analyzed using the Gaussian fitting, because the distance from the origin is inversely proportional d-spacing, so we can analyze d-spacing for the individual diffraction spots very carefully. And then, so this is a field of view that we have investigated electron diffraction from this sample. And in this field of view, there are two different microdomain bands, A and B, and each microdomain band is composed of the chaining of lamella-like nanodomains with two different orientations. So if we zoom up this area, here are two different microdomain bands, and each composes of two different nanodomains of two different orientations. So if we choose this round area for the electron diffraction, we can investigate the diffraction spot for electron diffraction for the nanodomains of 4 different orientations. And here's the result. This is an example of the observed diffraction spot for 2 bar to 0 spot. And by our careful analysis, we have found that there are 4 individual diffraction spots for this 2 bar to 0 spot. And then if we carefully analyze the distance from the center, from the origin, we have obtained that there are 4 different d-spacing for these 4 spots. So point is, how can we analyze this result? And then the point is, if the crystal structure is cubic phase, the 2 to 0 plane should have one identical d-spacing, so this shouldn't have 4 different d-spacings. Similarly, if the T phases for the R phases, they can have only 2 different d-spacings. So this result indicates that this result cannot be explained neither by T phases nor R phases. So it may be indicated that the crystal structure is of lower symmetric phases, such as monoclinic phase. So after based on our finding that our domain response and crystal phase analysis, we try to estimate the domain effect to the piezoelectricities. Here we very simply assume that without electric field, the specimen is equally divided into 1/3 for C-axis, B-axis, A-axis, parallel to the 001 direction, and when the electric field is applied, for entire the region becomes C-axis parallel to 001. Using this very simple assumption and reported lattice constant for monoclinic phases, we found that domain effect can be up to roughly 0.2%. And we have also found that the domain response is reversible. This explains experimentally reported low hysteresis curve. So we think that the domain effects may not be negligibly small, and this also explains low hysteresis in the field strength curve. And after we reported this sort of study, I got this sort of question or comment many times. Because the TM is in principle have a very high spatial resolution, why don't you carry out in-situ study at atomic scale? So we have tried this sort of experiments, and then so because of time, let me skip this movie, but my conclusion is that direct response cannot be observed at atomic scale. However, if we keep applying electric field for a long time, everything is stable, so we can observe atomic scale structure under electric field. So we have tried to evaluate how much we can measure the atomic position precisely under the electric field in this sort of in situ STEM experiment. And first, we have checked the precision of lattice constant measurement. And this is a measured STEM images under this much of electric field. And then this side is a result. For the first scan direction along this direction, we obtained the precision of about 4 picometers. On the other hand, along the slow scan direction in this way, it becomes slightly worse at 7 picometers. So we found that the precision of at worst 7 picometers can be achieved. And similarly, we have observed we can measure the position of titanium ion at 5 picometer accuracies. So we are currently applying this method to ferroelectric material, and here is the result ranging from plus 40 kilovolt per centimeter down to minus 30 kilovolt per centimeter, and these results are currently under analysis. Thank you very much.
Thank you very much. We have time for a few questions. I'll start with a question, actually. So you showed images under a static electric field. If you're changing the electric field while you're measuring, does that induce any kind of instability in your imaging? Or is it only, I mean, it's one thing to show it under static, but can you be varying the field and taking a picture at the same time, or is that more difficult to capture?
You mean for this result?
Yes.
This is, how can I say? This is step by step. Mm-hmm. So I applied this much, wait for minutes or 10 minutes or so, and then take images. Okay. And stop it, and apply this much, wait for a while, and take it. Okay. Repeated these sort of things. Yes.
Okay.
Yeah, it's a beautiful work, very useful for the community. I wonder whether you ever tried or thought about looking at thin films of PM and PT.
Not have thin film sample.
How thick was the sample you look in transmission?
It roughly 100 to 200 nanometer.
So in the PMNPT, do you see any chemical heterogeneity?
I have observed the formation of chemical order domain. It's very small, a few nanometer in size. Except for that, I haven't observed any chemical.
Okay, but do you see any then correlation in the polarization in the chemical order?
I don't know. I have no idea. Thank you very much.
And we'll take one more question while our next speaker comes up, please.
So for those nanodomains, are they in monoclinic phase or in a mixture of bromhedral and tetrahedral phase, based on your studies?
Because our study can measure only a very narrow region. So even in a narrow region, I believe that it's a single monoclinic phase. However, if you think about wider region, our study cannot tell everything.
Thank you again.
Thank you very much.
Thank you. Okay, thank you. So this is the last contributed talk of this session, and it will be given by Hiroki Yakota on three-dimensional observations of polar domain boundaries in ferroelastic materials. Thank you.
Thank you very much for the introduction. And today I'm going to talk about the polar nature of the domain boundary in ferroelastic materials. And we have a lot of talk about domain boundary in the morning, and they are always talking about the head-head and tail-to-tail domain boundary. But now I'm going to talk about the different thing about the domain boundary. So the major thing that I'm investigating now is ferroelastic material. So it's nothing to do with ferroelectric domain boundaries. So this is the outline of my talk today. I'm going to show you two examples of the ferroelastic material for our experiments. So now let me begin my presentation from the introduction. And as you know, the domain boundary becomes one of the hot topics in these days. And here I plot this number of the publication as a function of year. And as you can see that the number of publications related to domain boundary increases monotonically, and also it reaches almost about 30,000 according to the Web of Science now. So for a long time, domain boundary have been considered as a wall which separates the different domains, but now the situation is changing. So before, everybody is trying to grow a single crystal or untwinned crystal, but now the situation is completely changes. We are trying to use domain boundary. So because thanks to the development of the experimental technique, we are now able to measure the physical property as a domain boundary, and it completely changed our concept about the domain boundary now. So there are a lot of projects trying to use domain boundary for the application, and we call this tendency as domain boundary engineering. And because the density of domain boundary can be extremely high compared with domain itself, there is a possibility to use domain boundary for the high density memory devices and also microwave device and transducer and so on. So here I summarize some of the exotic property observed at domain boundary in these days. And for example, electromagnetic coupling and photovoltaic effect and superconductivity have been reported at domain boundary in various oxides. And among them, I'm now interested in the ferroelectric property observed at domain boundary in ferroelastic materials. So the polar nature of the domain boundary in ferroelastic material have been predicted in 2008 theoretically, and this group also tried to measure the polar nature of the domain boundary by using an aberration corrected TEM, and they reported a result in 2012. So what they really observed is the displacement of the titanium atom as a domain boundary. And according to the displacement magnitude of the titanium atom, they estimated the magnitude of the spontaneous polarization, and it is almost the same value with the normal ferroelectric materials. So this result is very attractive. However, there are some problems that we need to consider about this experiment. For example, in the case of TEM, they only observe one type of domain boundary, although there are several different domain boundaries in ferroelastic materials. And another thing is during the sample preparation, because this is a TEM measurement, so they need to prepare very thin sample by milling or polishing. So during this kind of procedure, ferroelastic material can be completely change its property or domain boundary structure. So I think it is necessary to investigate the crystal without any special treatment to conclude the polar nature of the domain boundary in the case of ferroelastic materials. So this is our motivation to investigate the ferroelastic material by using our method. So now I'm going to talk about the experimental technique and the results. So we use second harmonic generation as a probe for achieving our aim. And the second harmonic generation is a nonlinear optic effect. And when the incident beam enters into the crystal, it generates a second harmonic generation whose wavelength is half of the fundamental wave. So there are several advantages to use second harmonic generation for our purposes. And firstly, SHG is very sensitive to the change of the spontaneous polarization. And also, using our scanning system, we can obtain the three-dimensional images of the domain structure without any distraction. And thirdly, because SHG is related to the third-rank detensor component, we can determine the symmetry of the domain boundary. So it is very important and necessary to determine the symmetry because piezoelectricity is not enough to confirm the polar nature. So this is the optical system that we are using for our experiment, and we use MD-YBO4 laser as a fundamental wave, and we separate our optical system into two paths, and one path is for the fundamental wave, and the another one is for the reference wave. And for the reference wave, we normally use difference wave for the interference experiment to observe the 180-degree domain boundary, but this time, I'm not going to use interference experiment, so I'm only use a path one for our experiment today. So I will show you the first example about the ferroelastic calcium titanate. So this is a polarization microscope images of calcium titanate, and there are two different kinds of domain boundaries in these materials. One is almost parallel to the lateral direction, and this is a major domain boundary. And also there is another type of domain boundary which is about 45-degree incline from the another domain boundary. So we call this domain boundary as type A and type B domain boundary. And we selected this region and observed by using a second harmonic generation microscope. And the result is shown on the right side. And the white region corresponds to the SHG active area and black to the non-SHG active area. And as you can see, when we compare with the polarization microscope image, we can clearly see that the domain boundary is SHG active for type A and type B domain boundaries. So we selected the area where the type A domain boundary and type B domain boundary coexist and performed a three-dimensional observation. And this is a result for the three-dimensional observation. So we simply measure the two-dimensional images with different depths. And this is a constructed images of 3D image of domain boundaries. So as you can see that the type A and type B domain boundary, even inside the domain, even inside the specimen, it remains SHG active. That means these domain boundaries can be polar even inside the specimen. And also we did a polarization analysis to determine the symmetry of domain boundary. And in the case of type B domain boundary, it can be fit with a monoclinic M. And this symmetry belongs to the polar group. So we can conclude that the domain boundary of calcium titanate is a polar. And also, we try to apply the stress because if we want to apply domain boundary for the application, it is necessary to control the domain boundary and also its properties. So we did some kind of tentative experiment by making this kind of apparatus. So we use a screw to apply the stress like this. And when we use these apparatus and measure it under the polarization microscope, and this is the result. So we are applying the stress parallel to the lateral direction. So when we increase the magnitude of the strain, the new domain boundaries start to appear from the edge of the specimen. And when we further increase the stress, these domain boundaries start to propagate into the middle of the specimen. And we selected this area and carried out a second homogenization microscope observation, and this is a result for the SAG microscope observation. And as you can see, the newly appeared domain boundary by the stress is also the polar, and when we did the three-dimensional images, it's almost perpendicular to the sample surface. And also, the polarization analysis confirmed that the symmetry of newly appeared domain boundary is monoclinic M in the calcium titanate case. So now I will move to the second example about the lanthanum aluminate. So a lot of study, especially about the ferroelectricity, the domain boundary in ferroelastic material is limited for the calcium titanate. And when I show the calcium titanate result, everybody asked me, why don't you do the other material? Why don't you try to the other material? So we are trying to do the lanthanum aluminate now. And there is a report in 2016, and they reported that they observed the polar nature of the domain boundary in lanthanum aluminate. So what they really observed, they created a tweed pattern domain boundary and performed the PFM measurement also, and also the RPS measurement. And they observed some kind of signal from the tweed pattern domain boundary in the case of lanthanum aluminate. So now I'm not going to talk about the tweed pattern domain boundary. I'm going to talk about the natural domain boundary I can observe in the lanthanum aluminate. So this is a polarization microscope image of lanthanum aluminate. And you can see there is only one type of domain boundary in this material. And when we select this area, we can observe and we observed it by using a second homogenization microscope. And as you can see that it also, the domain boundary of lanthanum aluminate is also also the SAG active. And when we did the three-dimensional images, we can see that even inside the specimen, it remains SAG active. So we did a polarization analysis for this measurement to determine the symmetry of this domain boundary. And when we change the direction of the polarizer and analyzer, and you can see that there is no SHG intensity except the domain boundary in these materials. And we select some area and perform the fitting by assuming the symmetry as the trigonal 3M, and it fits the experimental data quite well. And so we analyze this data according to the strength compatibility theory. And in the case of ferroelastic material, there are two types of domain boundary, and one is so-called double wall, and the other one is double prime wall. And in the case of lanthanum aluminate, because the phase transition is from M/3M to MMM, there are 9 domain boundaries, and all of them belongs to the double wall, which is permitted by the crystallographical point of view. And the domain boundary that we observe this time is x equals 0 or y equals 0 domain boundary. So we confirm the polar nature of the domain boundary of lanthanum aluminate is polar in the case of double wall domain boundary. So now I will finish my presentation by summarizing my talks. So I show you 2 examples of the polar nature of the domain boundary in ferroelastic material. The first one is calcium titanate, and the second one is lanthanum aluminate. And both shows SHG active, and also this SHG activity is remain even inside the specimen. And thank you very much for listening to my presentation.
Thank you. So we have time for a few questions. I'll start by asking one. So you showed that you were applying force to the material to contract it. Do you have any type of estimate to how much you were changing the lattice constant by, or how, like?
No, okay. Unfortunately, no.
Okay, okay. Any other? guess everyone's quite ready for our coffee break. Oh, one question or no? Okay. Okay. Yeah. Okay.
What's the resolution of the SHG microscope?
Lateral reaction is about 500 nanometer, and the depth is 2 micron.
Well, maybe we'll thank all of our speakers again, and we have a half an hour break right now for coffee.